let's do a little bit of matrix methods just to prepare for next week. Okay, basic matrix has first of all the symbology. Unfortunately, this didn't come out too well, but that's a little arrow over a letter is the usual designation of a matrix. So, and that's only one of a number of different designations. One of them is kind of a double letter like that, which is really hard to portray, and PowerPoint didn't do a real good job of it. So what I prefer is this with the single barbed arrow over it, the designated matrix. A matrix has R by C, R rows and C columns. As a convention, the first subscript is which row it's in, and the second subscript is which column it's in. Okay, so row column. So that means that right here, A sub 2, 1 is row 2, column 1. 2, 2 is row 2, column 2, etc. Okay. A matrix that only has one element is called scalar. Scalar is a C-A-L-A-R, and that's just like any other number. So this is an example of two matrices. If you want to subtract or add matrices, they have to have the same number of rows and columns. And you simply add or subtract the elements of the matrices. Just like, so this would be B times A times A minus B, or I mean, this would be B minus A. A minus B is different, and that would look like 1 minus 9 is the first element. Second element is 2 minus 8. Third element, or second row, first column is 3 minus 7. And second row, second column is 4 minus 6. Okay, so that ends up to negative 8, negative 6, negative 4, negative 2. But it has to, the rows and column, number of rows and columns, the dimensions have to match. Same is true for addition. Addition and subtraction is pretty straightforward. If you multiply a scalar times a matrix, it's simply that scalar times each of the elements of the matrix. Okay. Again, very, very straightforward. So the scalar 2 times the matrix 1, 2, 3, 4 is simply 2 times each one of those elements, so it's 2, 4, 6, 8 is your result. Matrix multiplication is somewhat less straightforward. I have B times A here. Okay, so let's talk about matrix B times the matrix A. Okay, the matrix B has 2 rows, 3 columns, which you would designate as 2 by 3. So as rows by columns. The matrix A has 3 rows and 2 columns, so that would be 3 by 2. I know that I can add these together because the number of rows in B matches the number of rows in A. Okay? And I can infer from that B times A will be will give me a matrix, we'll call it C, which would be a 2 by 2 matrix. Which, when we do that, say we end up with a 2 by 2 matrix. Take the first element, to do the first element, this is the second element, third element, fourth element. Since it's B times A, it's first row times first column in the first element. So it's 9 times 1 plus 8 times 3 plus 7 times 5. For the second column, first row, it's 9 times 2 plus 8 times 4 plus 7 times 6. For the second row, first column, it's 6 by 1 times 1, 5 times 3, 4 times 5. Second row, second column, 6 by 2 plus 5 by 4 is 4 by 6. Right? If I were doing it the other way around, it was A times B. First let me prove that A times B is a tenable solution, or a tenable multiplication, A times B, because A is a 3 by 2, and B is a 2 by 3. That means that I'm going to end up with a 3 by 3. Here my C, I'll call it D, a different result will be a 3 by 3 matrix. And the 3 by 3 of A times B is first row times column, 1 times 9 plus 2 times 6. Then 1 times 2, 1 times 8 times 2 times plus 2 times 5. First row, third column, 1 times 7 plus 2 times 4. And then remember this is going to be a 3 by 3. So for the second row, 3 times 9 plus 4 times 6. Three times 8 plus 4 times 5. Three times 7 plus 4 by 4. And 5 for the third row, 5 times 9 plus 6 times 6. Five times 8 plus 6 times 5. And 5 times 7 plus 6 times 4. And so those are 9 elements. This is our D matrix. First, what that translates to is 9 plus 12 is 21, 8 plus 10, 18, 7 plus 8 is 15, 3 times 9 is 27, 4 times 6 is 24, so that's 51, I think. Addition very well in my head. 3 times 8 is 24, plus 20 is 44. Did I make a mistake? Nope. So far so good?
I just can't keep up.
21 plus 16
37.
is 37.
Nice.
5 times 9 is 45 plus 36. 45 plus 30 is 75, 81. 5 times 8 is 40. 70. Well, it's 40 plus 5 times 6 is 70. Thank you. And okay, so 35 plus 24, that's 55, 59, I think. So that's our 3 by 3 matrix that results from multiplying this 2.
You just tell you I don't like this already.
Well, this, I'm not going to test you on this, but you need to understand it so that you can understand the notation for the logistic for regression. And it will help you understand what's behind a program like SPSS or something like that. Okay. Okay. Rules for multiplication of matrices. I already demonstrated that B times A is not the same as A times B. Because remember, B times A was a 2 by 2, A times B was a 3 by 3. Not the same thing at all. Grouping, the associative law, does hold. I can take A and multiply it times the product of B and C and get the same thing that I would get if I multiplied A times B and then multiplied the product by C. I can distribute it. Just algebraically, I can distribute it in this direction. I can also distribute it in that direction. Transposition. You transpose something, rows become columns, columns become rows. So the first row, 1, 3, 5, our first column, becomes the first row. The second column becomes the second row. That's the process of transposition. The law of transposition says that I can take two matrices and multiply them by each other, transpose the result, and I would get the same answers if I transpose each one individually before I multiply them. Okay, so we talked about addition, subtraction, multiplication by scalar, multiplication of matrices, some laws that they conform to, and transposition. Next thing we want to talk about is determinants. Determinants is a way to, and there are many uses for determinants. And we'll talk about the use that we'll be interested in, but what you do with a determinant is it's a way of transferring it's a scalar representation of the matrix. A 2 by 2 determinant is simple, and notice the change in notation. I use square brackets on matrices, open brackets on determinant. For a 2 by 2, as I said, it's simple. It's the difference of the cross products. 1 times 4 minus 2 times 3. So the determinant of this small 2 by 2 matrix is minus 2. And the result is always a scalar of a matrix. For a 3 by 3 matrix or higher, you have to use cofactors because it becomes more complicated. Since we will be dealing with 3 by 3 or higher, let's talk about cofactors in finding the determinant of a 3 by 3 matrix. Again, square brackets to characterize the matrix. The straight open brackets to depict the determinant. First thing we need to do is choose a row or column. It doesn't matter which one. That's an interesting property of matrices. It doesn't matter which row or column you choose, and find the cofactors of that row and column. So let's take the first. And the reason I chose the first is because it has a 0 in it. Makes it simple if there's a 0. So if I were using this, I would choose either the first row or the third column to find my cofactors to get the determinant. So I've chosen the first row. Just writing it out, it's each element times its cofactor plus the next element times its cofactor plus the next element times its cofactor. As you can see, that 0 makes that term drop away and simplifies it. Okay. The cofactor. So this is the element. This is the cofactor. I think I better. The cofactor portion of this is this part right here. This is the cofactor portion. Here. This is the cofactor portion. Right here. Let's take a look at the first one. The first part of the cofactor is -1. I'll write the generic. The generic cofactor is -1, a constant. It's always -1, raised to the row plus column position of that element. So the row plus column position of this is row 1, column 1, 3. So that means that we take -1 and raise it to the 1 plus 1, row plus column. -1 to 1 to the squared is what? -1 squared is 1.
1.
Yeah. So really what this is a systematic way to determine whether or not it's positive or negative. And then we do the determinant of the submatrix. Okay. The submatrix for 3 is this. 2, 1, -6, 4. That's 2 by 2. So all we got to do is do cross multiplication. 2 times 4 minus 1 times 6. 8 minus 1 times 6 is plus 6. So that's 14. So that one becomes 14. So it becomes 3 times 1 plus 14. That's the first. And 5, this is row 1, column 2. 1 plus 2 is 3. So that becomes -1. 5 times -1. And then the submatrix. The submatrix of 5, if you draw a line through that row, through the same row, and a line through the same column, we get -1, 1, 3, and 4. There we go, -1, 1, 3, and 4. So we have -1, -1 minus 4, minus 1 times 3 gives us a -7. So that's 5 times -1, which is -5, times -7. So -5 times -7 is positive 35. So we have 42 plus 35 is 77. All right, just to demonstrate, which row or column should I use? Any row or column, just tell me. Some row or column of A, to show that it will give us the same answer.
3.
Column, so row 3? Did I hear 3?
Yeah.
So row 3, row 3, okay. Row 3 is 3, 6, 4. Okay, so we have 3, and then the cofactor of 3, plus -6 times the cofactor of -6, plus 4 times the cofactor of 4. So, the power, what is this? This is row 3, column 1, right?
Mm.
So it's 3 plus 1 is our exponent. The submatrix for 3, if I draw a line through the same column, a line through the same row, is 5, 0, 2, 1. So it's determinant 5, 0, 2, 1. Negative 6. That is row 3, column 2. That's negative 1 to the 3 plus 2. And submatrix, I draw a line here. Here it's 3, 0, negative 1, 1. And then negative 1 here to 4 is row 3, column 3. So I better be doing my arithmetic right, or this is not going to turn out right. Okay, so the submatrix for 4 is 3, 5, negative 2, 1.
Negative 1, 2.
Negative 1, 2. See? I do it to myself.
Are you okay?
You said it wrong, but I was hoping you got it right.
I just. Okay. So, 3, carry 3 down, negative 1 to the 4th is just 1. 5 times 1, 5 times 1 minus 2 times 0 is 5. Plus, and we have negative 6 times negative 1 to the 5th, it's still negative 1. This is 3 minus 0. It's 3 plus 4 times negative 1 to the 6th is 1. And here we have 3 times 2 is 6, minus negative 5 is 11. Okay. 15 plus 18 plus 44. And that should be 77, so let's see whether it adds up to 77. 5 is 13, and 4 is 7. So far so good. 7, that's 2, 3, and 4 is 77. It's identical, doesn't matter which row or column you use. Yeah.
I have a question. Where it says 3 minus 1, 1 over 1, and it's the first bracket, the 2, 1 minus 6, 4, on the actual slide.
Oh, here, okay.
Is that supposed to be minus 1? Because we have a positive 6, and it's 1 times negative 6.
Yeah, because it's 2 times 4 is 8, minus negative 6.
Oh, okay, that's why.
Yeah, because the determinant, remember, is the difference in cross products.
That's right.
Yeah.
Took me a second. I was wondering where I was missing something.
Okay. I say we should probably stop there. And I'll finish this next week and go into, and then into logistic regression. I will probably finish logistic regression next week, so we'll have plenty of time in 2 weeks to do the review and all the practice problem set and everything. But I'll start out with the problems, the homework associated with today's lecture. Okay? Questions on anything? Like the universe and everything else. Okay. I'll see you next week then. Thank you.
Thanks, Max.
Back.